Now we want to start talking about one of probably the most important principles in all of physics, and that is the conservation of momentum. Now we've already met one conservation law before, and that was the conservation of energy. And the conservation of energy held when we had no forces like friction or air resistance. We call them dissipative forces in our system. Conservation of momentum, on the other hand, is a little bit more foundational because go back to Newton's third law, and remember that Newton's third law says for every force, there is an equal and opposite force. Okay, so mathematically we can write this as, let's say we have two objects putting forces on each other, and we would say that the force on object 1 due to the interaction with object 2 is going to be equal in magnitude but opposite in direction to the force that object 2 puts on object 1. And if we go back to the definition of force using the idea of momentum, this is the change in momentum that one experiences due to the interaction of two over the time interval over which the force acts is going to be equal to the change in momentum that 2 experiences as a result of its interaction with 1 over the same time interval, because the time intervals must be the same. The two forces are exerting, or the two objects are interacting with each other. They're both going to interact for the exact same amount of time. So what this means is that the change in momentas are equal. So this applies when there are no outside forces acting on my system. No outside forces, period. Not just dissipative forces like friction or air resistance, but no outside forces, period. And what do I mean by no outside force? Okay, so an outside force would be a force that I did not take into account when I set up my initial system. Okay, that is what we mean by no outside forces. Okay, now conservation of momentum generally applies to things like collisions. And we have two types of collisions. Okay, we have elastic collisions and inelastic. And elastic collisions, the formal definition of elastic collisions, are collisions where momentum is conserved and kinetic energy is conserved. Inelastic collisions are where only momentum is conserved. Okay, energy is not. Now, there's a really easy way to think about these in situations you've seen before. Elastic collisions are collisions that typically the objects bounce off of each other. And this would be something akin to, say, the bouncy balls that people play with. Those are often more or less elastic collisions. Billiard balls are more elastic than not. So there's a few situations where we'll run into elastic collisions. Inelastic collisions are where the objects stick together. Okay, so in elastic collisions, even though we can do some things mathematically with these ideas. Momentum is conserved and kinetic energy is conserved, whereas in the inelastic case only momentum is conserved. More or less, all we really need to know for the purposes of determining whether they're elastic or not is, do they bounce off of each other or do they stick together? Okay. So let's do an example of an elastic collision where I have a block, and we'll let this be mass 5 kilograms, and it's at rest. And we have another block of exactly 5 kilograms, and its initial velocity is, say, 10 meters per second. And they collide, and I'll let this be block 1 and this be block 2. Okay, so we'll have the 1 subscript here and we'll have the 2 subscript here. Let me write that a little bit better. Okay. If these collide elastically, what will block 2's final velocity be? Okay, if they collide inelastically, what will block 2's final velocity be? So the conservation of momentum, if we go back here, okay, the conservation of momentum says that the changes in momenta are equal, and what that means is that total momentum does not change. Okay, total momentum does not change. And mathematically we can write this as Pi equals Pf. Whatever the total initial momentum in the system is, it's going to be equal to the total final momentum of that system. So going back to this, our P1I is going to be equal to our M1 V1I, and P2I is going to be equal to M1 V2I. Okay, so Pi is going to be equal to the sum of these, right? And this must then also equal the final momentum. And so, if Pi equals Pf, the way we can write this is that M1 V1I plus M2 V2I must equal M1 V1F plus M2 V2F. Okay? This is the general equation for the conservation of momentum for an elastic collision. Okay, this is the general equation for the conservation of momentum for an elastic collision. Now, first things first, in this case, if I send, and again we're assuming no friction, if I send block 1 in to collide with block 2, and they both have the same mass, then something interesting happens, and what I can do is drop my mass subscripts because they're all the same, and they'll simply cancel out. If I divide both sides by m, this is what I get. So V1I plus V2I equals v1f plus v2f. But we also can simplify this particular situation further because we know v2i is 0. So that goes away, and we now have v1i is equal to v1f plus v2f. Now, just based on this situation alone, one might be tempted to think that both blocks continue moving, only both with half the speed of the original block. And that is a tempting answer, but remember that energy must also be conserved. For an elastic collision, energy must also be conserved, so that means that the initial kinetic energy of the first block must equal the final kinetic energy. Okay? And this is why elastic collisions are a little bit more difficult mathematically, because we have to take both of these equations into account. But it turns out, okay, that again, if the masses are equal, I can cancel them all out. And I'm just again left with 1/2 v1i squared equals 1/2 v1f squared plus 1/2 v2f squared. And I can get rid of the 1/2s. I can multiply both sides by 2. And we get v1i squared equals v1f squared plus v2f squared. The only way for these two equations to be true, we won't go through the derivation, but the only way for these two equations to be true is if v1f equals 0 and v2f equals v1i. Okay? That's the only way for both of these conditions to be true. And what this means is that the second block gets all of the velocity of the first block, and the first block stops. So if we were to draw a second diagram, well, we'll draw it over here, right? If we were to draw a separate diagram, here's the first block coming into the second block, which is at rest. And after the collision, we have the first block at rest, and the second block is now moving with the velocity of block 1. Okay? So you encounter this in things like billiards. If you hit the cue ball straight on, dead center onto another ball, another billiard ball, then the cue ball will stop and the other ball will continue rolling in that same direction. So what about for an inelastic collision? And one of the classic examples here is car wrecks. Okay, and in the inelastic case, we still start out with our conservation of momentum equation. The initial momentum equals the final momentum. And here, if we have two objects, m v1i plus m v2i, the initial momentum will be the initial momentum of both objects. But if they stick together, then they're going to move with some final velocity that's the same. So we can write the final momentum as the sum of their masses times whatever their final momentum is. So let's look at an example here, and this time let's have to use the vector nature of momentum. I did not mention that, I guess, in the last video. Momentum is a vector, okay? That's one thing we need to stress. Momentum is a vector. So P is a vector, okay? So imagine, I'm not going to be able to draw this terribly well, but we'll do our best. Imagine that we have two football players, and there's a wide receiver with the football, and here's my cheesy attempt to draw a helmet, is running this way, and here we have a larger linebacker moving this way, and let's let the wide receiver have a mass of about 60 kilograms, and he'll have an initial velocity of 8 meters per second. And the linebacker, with a mass of 75 kilograms, has a velocity of 5 meters per second. Okay, so the wide receiver can outrun him, but if they're running head-on into each other, we want to know what is the final momentum of the system, right? Will the wide receiver be able to lunge forward while being tackled, or is the linebacker going to drive him back? And so what we can do is say m1 v1I plus m2 v2I must be equal to m1 plus m2 quantity times the final velocity. So our wide receiver was 60 kilograms, and he had a velocity of 8 meters per second. And let's go back here and let's define our coordinate system so that to the right is positive and backward is negative, or to the left is negative. And so our linebacker, while having 75 kilograms, is going to have a velocity of -5 meters per second. Okay, so this is the initial momentum of the entire system. Right, the initial momentum for the entire system. And so the initial momentum for the entire system is going to be, well, 8 times 60 is going to be 480. And 75 times 5 is -375 kilograms times meters per second. So the total momentum for the system is going to be, what, 105? Kilograms times meters per second. So what is the final velocity of the collision going to be, or after the collision going to be? So what we can do is say that 105 kilograms times meters per second must be equal to 60 plus 75 times VF. And if we add up 60 and 75, we're going to get 135 times the final velocity. So the final velocity This will be 105 divided by 135. And our numerator is going to have kilograms times meters per second. And our denominator is just going to have kilograms. And our kilograms cancel. And 105 divided by 135 is going to be 0.78 meters per second. So the linebacker more or less has done his job. At this point, he's probably going to be able to tackle him and drag him down. But the wide receiver will probably be able to lunge forward under these conditions. So that is how you determine the final velocity for an inelastic collision. Okay. Now, one last topic we want to talk about is the issue of recoil. And recoil is precisely the inverse of an inelastic collision. Okay, so if we think about it, if we have some sort of rifle or some sort of firearm here, right? And we have a bullet inside, and that bullet is fired with some initial velocity, v bullet initial. We know from experience that the gun is going to recoil and fire backward. Well, it's not going to fire backward, but it's going to move backward. And so this is going to be the velocity of the gun. And in fact, actually, I'll drop the initial subscripts, and we'll just use velocity of the bullet and the velocity of the gun. So how fast will the gun recoil? That's the question. And to answer, we use the conservation of momentum. Okay, use the conservation of momentum. And again, to start out, we write down that Pi equals Pf. But if we go back to the case of the gun, what is Pi and what is Pf? So Pi is the initial momentum before firing. So if neither the bullet nor the gun have any velocity before the bullet is fired, then the total momentum is 0. So the initial momentum is 0. And the final momentum, the bullet is going to go this way, the gun is going to go this way. So if we define this direction to be positive and this direction to be negative, and in this case it really does not matter which direction you make positive and negative. That is completely up to you. But I typically make positive to the right, unless for some reason it's a little more convenient. But again, in this case it really doesn't matter. So this is going to be the mass of the bullet times the velocity of the bullet minus the mass of the gun times the velocity of the gun. Okay, so the final momentum is going to be the vector sum of these two quantities. Now, as you can see, with the minus sign here and the left side equaling 0, we can immediately say that the mass of the gun times the velocity, or the recoil velocity of the gun, must be equal to the mass of the bullet times the muzzle velocity of the bullet. And just to give some round ballpark numbers here, let's say that this is maybe a 223, and the mass of the bullet, let's say the mass of the bullet is right around 5 grams, or 0.005 kilograms, and the velocity of the bullet is right around 400 meters per second. And let's say that the mass of the gun is maybe 2 kilograms, and the velocity of the gun is what we want. We want the recoil velocity. Well, going back to this equation, if I just divide both sides by mg, or the mass of the gun, then that'll give me the recoil velocity. So Vg is going to equal the mass of the bullet times the velocity of the bullet divided by the mass of the gun. And so this is going to be 0.005 times 400 divided by 2.0. And I've dropped the units for convenience. I'm running out of room over here. But what this calculation turns out to be is 1 meter per second. Okay? So the gun is going to recoil back at about 1 meter per second. Now, that's enough, high enough that I at least wouldn't want to be in the way of that. And that's why, you know, there's several injuries per year because people mishandle their firearm. They don't properly brace it against their shoulder, and they can do damage to their shoulder, maybe even tear a muscle if they're not very careful. Whereas what happens if you make your mass part of the system? In other words, if you brace the gun up against your shoulder so that your mass and the gun's mass are essentially added, in that case, the mass of a person is going to be anywhere between typically 60 and 80 kilograms. And so now the mass of the gun goes up to, let's say, 62 kilograms. And if we do that same calculation, the velocity of the bullet times the mass of the bullet is actually equal to 2.0 kilograms times meters per second. And if we divide that now by the new 62 kilogram mass, instead of just the 2.0, we get a value of 0.03 meters per second. So when you brace the gun properly, it comes back at you at a very negligible speed that is hardly dangerous at all. So properly bracing your firearm is crucial. Now, I have one more question for you, maybe one more example. Okay? Imagine you have a brick wall. And you toss a tennis ball very fast with an initial velocity VI. And you're close enough to the wall that it bounces off and it really doesn't lose any velocity. But it's in the opposite direction. Okay? So VF is equal to negative VI. It's going in the opposite direction. Is momentum conserved in this case? Okay, I will leave that for you to think about, and then I'll answer it at the beginning of the next video. And in the next video, we will start off with, we'll start off with this, and then we will get into Chapter 8. All right, see you then.